A star blinks in the dark, and every blink arrives too late, not seconds late, not even a little late. It waits 44 full minutes, then flashes again as if it is keeping a secret. Right now, people with some of the best telescopes on Earth still cannot tell us why. If strange true stories like this are your kind of thing, subscribe now. We go after the real mysteries with the real science still attached. And this one gets harder to explain every time a new clue appears. For a long time, astronomers thought they understood this part of the sky. Stars explode, stars collapse, stars cool down, and their leftovers follow known rules. A dead star can still shine, spin, pulse, and throw out energy. But even the weird ones usually fit into a box with a name on it. Some dead stars become neutron stars, which are so packed with matter that a spoon of them would weigh more than a mountain. That sounds wild, but the main point is simple. They are tiny, heavy, and often spin very fast. When they send out beams of radio energy, we call many of them pulsars. A pulsar works a bit like a lighthouse. It spins and a beam sweeps across space. If Earth happens to sit in the path of that beam, we see a repeating flash. The gap between flashes tells us how fast that object is turning. Most pulsars are quick. Some spin every second, some much faster, and some whip around in tiny fractions of a second. Even the slow ones usually take only a few seconds to complete a turn. That is why astronomers built many of their ideas around speed. Then there are magnetars. These are also dead stars, but with magnetic fields so strong they can twist matter and light in brutal ways. They can flare, crack, and act strange for a while after violent outbursts. So when something odd appears, magnetars are often one of the first suspects. White dwarfs are different. They are also star remains, but they come from stars that were not massive enough to become neutron stars. The white dwarf is about the size of Earth, not a city. It is dense, hot at first, and then slowly cools over huge stretches of time. For years, those were the rough boxes. Fast radio pulses from pulsars made sense. Harsh, strange bursts from magnetars also made some sense. White dwarfs had their own expected behavior too. The sky was still full of puzzles, but the rulebook mostly held. And then a new kind of signal started poking holes in that rulebook. Not one strange flash, but a rhythm. Not random noise, but something that repeated again and again. And the repeat time was so slow that it should not have worked. The first big shock came from objects now called long-period radio transients. That name sounds technical, but it just means radio sources that pulse slowly over many minutes or even hours. Astronomers began finding them only in 2022. The strange part was not just that they existed, but that they seemed impossible. A normal pulsar is expected to stop making strong radio beams if it spins too slowly. That is one of the basic ideas in this field. So when researchers found sources pulsing every 18 minutes or 22 minutes or even longer, the warning lights came on. Something in the model was wrong or something in the sky was new. One of the early famous cases was Gleam-XJ 162759.5-52350.4.3. It had a period of 18.18 minutes. That alone was enough to make people stop and stare. A source like that did not fit cleanly inside the usual pulsar story. Then another object pushed the mystery even further. Astronomers found GPMJ 1839-10 pulsing every 22 minutes. And that is 1,318.1957 seconds between pulses, measured with striking precision. And old data showed it had likely been doing this since at least 1988. That mattered for a simple reason. A temporary glitch is one thing. A short, strange event after some cosmic blast is another. But a signal that keeps returning across decades is not easy to wave away. It begins to look like a stable system, not a brief accident. Scientists expected a very slow neutron star to have trouble making radio beams at all. What they found was a source calmly pulsing for years and years. That gap between expectation and reality is where the mystery grew teeth. The object was not just odd, it was stubbornly odd. Now hold on to that feeling because this is where the story turns sharper. Did you already know the sky could break its own rules like this? If not, tap like, drop your first guess in the comments, and subscribe before the next clue lands. By the time astronomers were still wrestling with those earlier long-period signals, a new object stepped forward. Its name is ASCAP-J 1832-0911, usually shortened to ASCAP-J 1832. It was studied using the ASCAP radio telescope on Wajari country in Australia, and almost from the start, it looked like trouble. ASCAP-J 1832 sits about 15,000 light years from Earth. That means the light reaching us now left when human history looked very different. Yet what matters is not just the distance. What matters is that this thing pulses in a pattern that should not be easy to produce. The radio signal from ASCAP-J 1832 rises and falls every 44 minutes. That is not a typo. 44 minutes is thousands of times longer than the repeated changes seen in many pulsars, which can flash multiple times each second. It is like comparing a hummingbird wing beat to a slow clock in an empty room. If the story stopped there, it would already be strange, but then another telescope joined in. NASA's Chandra X-ray Observatory looked at the same object, and it found that ASCAP-J 1832 was also varying in X-rays every 44 minutes. That was a huge moment. It was the first time an X-ray signal had been found in a long-period radio transient like this. So now the object was not just pulsing in radio waves, it was pulsing in radio and X-rays together. That raised the stakes immediately. Radio waves tell one part of the story, X-rays tell another. When both rise and fall on the same clock, astronomers learn that whatever engine drives the object is doing more than one thing at once. That makes some ideas stronger and others much weaker. And in this case, the easy ideas started falling apart. The accepted version of the paper describing this work was linked in 2025, and the results were published in Nature. The lead author was Dr. Ziteng Wang from Curtin University in Australia. Other researchers involved included Dr. Nanda Rea in Spain and Dr. Tong Bao in Italy. These were not casual guesses. This was careful work from people who know these objects well. They also noticed something else that made the case even stranger. Over the course of 6 months, the object faded hard. Using Chandra and ASCAP, the team saw that ASCAP J1832 dropped off in both radio waves and X-rays. So the mystery had two clocks, not one. First there was the 44-minute beat, then there was the slower change across months. That combination is what pushed the object beyond familiar territory. A repeating pulse is one puzzle. A repeating pulse plus a dramatic fade is a much nastier one. In February 2024, Chandra detected ASKAPJ1832 in X-rays during 2 observations. At that time, the source was unusually strong in radio waves as well. Then a third Chandra observation came in August 2024. By then, the radio source was about 1,000 times fainter than it had been in February, and in that August observation, Chandra saw no X-rays at all. That did not mean the object vanished. It meant the X-ray emission had dropped below what Chandra could detect. From that missing signal, the team concluded the source had dimmed by at least a factor of 10 in X-rays, so the system was changing in a major way. Here is why that matters in plain language. If you are trying to identify an object, you do not just ask what it does once, you ask how it behaves over time. Some cosmic objects are steady, some flare once, some fade slowly, and some pulse with machine-like regularity. ASKAPJ1832 seems to combine several personalities at once. At first glance, a pulsar sounds like the obvious answer. It pulses after all. That is the classic behavior people learn about first. But astronomers compared ASKAPJ1832 with the known radio and X-ray strengths of normal pulsars. And the match was poor. A neutron star pulling gas from a companion star was another idea. That sort of system can shine in X-rays because falling matter gets very hot. But once again, the numbers and behavior did not line up well. The radio and X-ray intensities were off. The object did not act like a standard member of that family either. Then comes one of the more tempting explanations. Maybe it is a magnetar, a neutron star with an extremely strong magnetic field. Some parts of ASCAP J1832 do seem to fit that idea. In fact, the team said an old magnetar more than 500,000 years old could explain part of the picture, but only part of it. The trouble is the radio emission. For a relatively old magnetar, ASKAPJ1832 is too bright and too variable in radio waves. That is not a tiny detail. That is the kind of mismatch that can sink a theory. A model that explains half the facts but fights the other half is not a finished answer. Then there was the location on the sky. SKAPJ1832 appears to sit inside a supernova remnant, which is the cloudy debris left after a star explodes. That sounds important because supernova remnants often hold neutron stars. So at first this looked like a useful clue. Maybe the dead star and the wreckage belonged together, but the team tested that idea too. Their conclusion was cold and simple. The overlap is probably just a line of sight coincidence. In other words, the object and the remnant only appear close together from Earth. They may not be related at all. If that is true, a major support beam for the neutron star idea gets weaker. You no longer get to say, there is the exploded star and there is its leftover core. Instead, you are back in the dark with a stranger object. And once more, the case opens up rather than closes down. And that is how a mystery deepens. What would throw your guess off more, the 44-minute pulse or the missing X-rays 6 months later? Tell me which clue feels stranger to you, then subscribe if you want more real space mysteries that do not end neatly. Because from here, the puzzle stops being about one weird signal and starts becoming about what dead stars can even do. At that point, researchers had to widen the search. If it was not a normal pulsar and not an easy accreting neutron star and not a clean magnetar match, what else remained? One possibility was an isolated white dwarf, but that did not fit the data well either. A lone white dwarf is dense and interesting, but it does not naturally explain everything seen from ASKAPJ1832. So the idea shifted. Maybe it is not alone, maybe it is a white dwarf with a companion star. That sounds promising until the magnetic field enters the story. And to make the white dwarf idea work, the object may need the strongest magnetic field ever known for a white dwarf in our galaxy. That is not a small adjustment. That is like fixing a puzzle piece by reshaping the whole edge. Yes, it might fit, but then you are forced to accept something else extreme. This is the repeating pattern that makes the whole topic so gripping. Scientists expect one kind of object. They observe something that partly looks like that object. Then one hard fact knocks the idea sideways. Every path forward seems to solve one problem and create another. And that is not drama added for effect. That is the real shape of the evidence. ASCAP J1832 is not annoying because it is noisy. It is difficult because it is precise. It keeps giving a regular rhythm without revealing the engine behind that rhythm. An independent team led by D. Lee from Tsinghua Tsinghua University in China also discovered the same source with the Daocheng radio telescope. They submitted their paper to Arxiv on the same day as the team led by Dr. Wang, but they did not report the X-ray behavior that Chandra saw. That made the X-ray result even more important. When two teams find the same source, confidence in the source itself goes up. You are less likely to be fooled by a bad reading or a one-time error, but when only one data set adds a crucial new clue, the argument becomes sharper. Now, the mystery is not only what is pulsing, it is also what kind of system can pulse this way in both bands, and here is the detail many people miss. The object did not merely blink and wait, it changed state over months. That means astronomers are not just hunting a fixed machine in space, they may be watching a changing system, a process, maybe even a cycle we still do not fully see. That is a very different kind of challenge. To understand why this matters, it helps to step back to the other long-period transients. Remember GPMJ 1839-10, the 22-minute source that appears to have pulsed since at least 1988. In 2026, a new study offered a possible way forward, not a final answer for everything, but a very important clue. That study argued that GPMJ 1839-10 may be a white dwarf star with a small companion known as an M dwarf. An M dwarf is just a common, smaller star about half the mass of our sun. The idea was that the white dwarf's magnetic pole sweeps through the companion's stellar wind. That interaction could help create powerful radio beams. Instead of a lonely spinning object, the source might be a binary system, meaning two stars orbiting each other. And the radio pattern was not random at all. Researchers found that the pulses came in groups of 4 or 5. Those groups arrived in pairs separated by 2 hours. Then the whole pattern repeated every 9 hours. That kind of stable heartbeat strongly suggested orbital motion. Two objects circling each other can create repeating changes in what we see from Earth. Using data from ASCAP in Australia, Meerkat in South Africa, and the Very Large Array in the United States, the team tracked the signal around the world. As Earth turned, one telescope could hand the source off to the next. They refined the orbital period to a precision of just 0.2 seconds. That is an astonishing level of detail for an object so far away. And it pushed the idea that at least some long-period transients are not neutron stars at all. They may be white dwarf systems wearing a very strange mask. That changed the larger conversation. By 2025, according to that 2026 report, 2 long-period transients had already been conclusively identified as white dwarf and M dwarf binaries. That was unexpected. Before that, many people naturally leaned toward neutron stars. Now white dwarfs were forcing their way into the center of the story. The old boxes were being relabeled in real time. So does that solve ASCAP J1832? Not yet. It offers a path, not a verdict. A binary white dwarf system might explain some long-period transients, but ASCAP J1832 still has that odd mix of radio pulses, X-ray pulses, and strong fading over months. Its full behavior remains hard to pin down. That is why this next question is so important. Do you think the answer will turn out to be a broken old theory or a completely new type of object? Leave your guess in the comments, hit like if this twist surprised you, and subscribe so you do not miss where the evidence points next. Right now, astronomers are not treating ASCAP J1832 like a solved case waiting for paperwork. They are treating it like an active crime scene in the sky. Every new observation matters, every missed pulse matters too. Researchers want to know whether the 44-minute pattern stays locked over long stretches of time. They want to see whether the source flares back up after fading. And they want to know if the radio and X-ray signals always rise together or if one can lead the other. Those details can reveal what kind of engine is hiding there. They are also looking for more objects like it. That matters because one mystery object can be a special case, but a whole group of similar objects becomes a class, and once you have a class, patterns begin to show. Patterns are how science starts turning confusion into understanding. Dr. Tongbao put it in a very human way. Finding a mystery like this is not frustrating. It is what makes science exciting. That sounds simple, but it matters. Science does not only move forward when a theory works, it also moves forward when reality says no. Dr. Nandareya said the team looked at several possibilities involving neutron stars and white dwarfs, either alone or with companion stars. So far, nothing matches exactly. That one word exactly tells the whole story. There are partial fits everywhere. There is no clean win anywhere. This is why the object feels so unsettling. Nature is usually under no duty to make itself easy for us, but we still expect some family resemblance. SKAPJ 1832 keeps showing traits borrowed from different cosmic families. It is like hearing one voice speak in several accents at once. Even the place where it was studied says something about modern astronomy. The ASCAP telescope sits on Wajari country in Australia. Chandra orbits above Earth and watches the universe in X-rays. Meerkat in South Africa, the Very Large Array in New Mexico, and the Daocheng radio telescope in China all feed the bigger hunt. This is a global effort stitched together by shared confusion, and still the object has not given up its name. If it is a magnetar, it behaves unlike the old ones people know. If it is a white dwarf, it may require an extreme magnetic field. If it is a binary, the exact structure is still uncertain. And if it is something else, then space has quietly introduced a new character. Here's another reason scientists are so careful. They have seen weird objects before that later turned out to be more ordinary than first believed, so they do not want excitement to outrun evidence. That is why papers compare radio strength, X-ray strength, timing, age, and possible companions in such detail. The mystery is real, but the standards stay hard. Still, we are already beyond the point where this can be dismissed as a minor oddity. A 44-minute radio pulse is not normal. A matching 44-minute X-ray pulse is even less normal. A dramatic 6-month change makes the problem larger still. 3 strange facts stacked together are hard to ignore. Now comes the part that reaches beyond one object. If ASCAP J1832 turns out to be a white dwarf system, then white dwarfs may be able to create kinds of pulsing behavior many people did not expect. If it turns out to be a magnetar after all, then our ideas about old magnetars may need major repair. Either way, the textbooks lose some comfort. What matters more to you, the mystery itself, or the chance that it could rewrite what we thought dead stars were able to do? Tell me below. And if you like clear science without the nonsense, subscribe and stay close to this story, because the next observation could favor one idea and crush another. Think about how science usually feels from the outside. People often imagine that experts know the answer first and explain it later. But that is not how moments like this look from the inside. From the inside, it looks like a room full of smart people holding pieces from different puzzles. Each piece is real. The final picture is missing. SKAPJ1832 is important because it shows us the edge of our map, not the center where everything is familiar. The edge where categories blur and old rules go soft. When a star pulses too slowly, the universe is not just being weird, it is pointing at something we have not understood yet. There's also a lesson in the timing. Long-period radio transients were only discovered in 2022. That means this is a very young field. We are not talking about a mystery people have been mapping for 100 years. We are watching the first chapters being written now, and the numbers involved make the point even stronger. Some of these objects have periods from 18 minutes to more than 6 hours. Regular pulsars, slowest in the common picture, rotate in only a few seconds. That is a huge gap. A gap that big often means you are dealing with a different engine, not a stretched version of the old one. The first confirmed white dwarf pulsar was only confirmed in 2016. That alone reminds us how fresh some of these ideas are. The sky can hold entire behaviors we have barely cataloged. We often act as if the universe is mostly known, but known is not the same as finished. One reason this topic spreads so far beyond astronomy is that it touches something very human. We hate patterns without explanations. If a light in your house flickers every 44 minutes, you do not ignore it. You start thinking, a machine is failing, a timer is hidden, or something deeper is wrong. Now scale that instinct up to the cosmos. A star is pulsing like a clock, but the clock does not match the known machines. That is why people keep returning to this story. It is not only about distance and radiation, it is about the shock of meeting order without understanding its source. There is also the question of what we are not seeing. Maybe ASCAP J1832 has a companion star too faint to notice easily. Maybe geometry is fooling us and the beam only reaches Earth under certain conditions. Maybe there are bursts or colors of light we have not caught yet. In astronomy, missing data can be as important as the data you have. That is why future observations matter so much. A deeper look in visible light or infrared could reveal a companion. A new X-ray detection during another bright radio phase could tighten the case. More examples of similar objects could expose a repeating blueprint. Mysteries usually break when one more clue arrives from a direction nobody expected. And there is an even larger possibility. Maybe long-period radio transients are not one thing. Maybe the label covers several different kinds of systems that only look similar at first glance. Some could be white dwarf binaries, some could be unusual neutron stars, and some may belong to a category we have not named yet. That would explain why no single model neatly fits every case. And it would also remind us that nature does not arrange itself for our convenience. Humans like clean shelves. The universe likes overlap, exceptions, and strange cousins. SKAPJ1832 may be sitting right where several cosmic stories meet. If you were an astronomer and had one night on a major telescope, would you spend it chasing this object? Answer that in the comments. Leave a like if you would, and subscribe if you want to follow mysteries while they are still unsolved. Because some of the most exciting stories in science are the ones still moving. There is another emotional layer to all this. Dead stars are not supposed to feel active in the way living things do. Yet these objects flash, fade, pulse, and interact. They feel restless. They remind us that death in space does not mean silence. Sometimes it means a second life with stranger rules. Our own sun will become a white dwarf one day, though not one like the most extreme ideas in this story. That future is billions of years away. Still, when scientists ask what white dwarfs can do, they are also asking about one possible fate of stars like ours. The question is distant but not alien to us. Neutron stars, white dwarfs, magnetars, binaries, remnants, winds, beams. These words can sound cold at first, but underneath them is a simple human effort. We are trying to understand what survives after a star dies and what those remains are still able to say. SKAPJ1832 is saying something loud. We just do not speak the language yet. That is why the dates matter. February 2024, bright and active. August 2024, much fainter with X-rays gone from view. A paper in Nature in 2025. A wider white dwarf clue from another long period transient in 2026. This is not old history. This is an active unfolding case. Every time a new object like this is found, astronomers compare it against the growing list. How long is the pulse period? Is there X-ray light too? Does the source fade or hold steady? Is there evidence for a companion star or for a magnetic field strong enough to twist the old rules? The answer to those questions will shape more than one paper. It will shape how future surveys search the sky. If researchers know what signs to watch for, they can find more of these objects faster. And once the sample grows, the mystery starts losing places to hide. One object can lie to intuition. 10 objects begin telling the truth. So yes, this is a story about one pulsing star, but it is also about how science changes, not in one giant leap, but in stubborn little corrections. A 44-minute pulse here, an X-ray match there, a 6-month fade that refuses to go away. That is how a field bends. The biggest surprise may be that the universe did not need to invent some impossible magic to confuse us. It only needed to place a familiar kind of dead object in an unfamiliar setup or let an old process run under extreme conditions. Sometimes mystery is not fantasy, sometimes it is ordinary matter arranged in a way we had not imagined. Even so, we should not pretend the ending is close. Scientists are still hunting for clues. They are still testing neutron star ideas against white dwarf ideas. They are still checking whether the apparent supernova remnant link means anything at all. ASCAP J1832 remains open, active, and deeply strange, and maybe that is the best part. For once, we do not have to look back at a solved chapter and admire how clever the final answer was. We get to stand in the middle of the uncertainty. We get to watch smart people argue carefully with evidence. We get to feel the shape of real discovery while it is still unfinished. If ASCAP J1832 turns out to be a new twist on a white dwarf binary, it will still be amazing. If it turns out to be an old magnetar breaking our expectations, that will also be amazing. And if it turns out to be something stranger than either of those, then this story may become one of the key moments in modern radio astronomy. No matter which answer wins, the road there is already teaching us something. It is teaching us that the sky still has rooms we have barely entered, that a pattern can sit in data for years and still resist explanation, and that better instruments do not end mystery. They often sharpen it. The clearer we see, the more honest our confusion becomes. So when you hear that a star is pulsing in a pattern no one can explain, that is not clickbait if the details hold up. A 44-minute rhythm in radio waves matching X-ray changes on the same rhythm, a dramatic fade across 6 months, and no model that fits comfortably without asking for something extreme. That is why this matters even if you never study astronomy. It is a reminder that reality is not done surprising us. The world beyond Earth is not only beautiful, it is still unfinished in our minds. There are still true things out there that we do not know how to name, and maybe that is what makes a mystery worth following. Not just the promise of an answer, but the chance to see knowledge being built. Brick by brick, observation by observation, one impossible pulse at a time. If you want to stay with stories like this as they unfold, subscribe and turn on notifications. And tell me this in the comments. What do you think ASCAP J1832 really is? An extreme white dwarf system, an old magnetar, or something nobody has named yet? If this mystery grabbed you, share it with someone who loves space and strange true questions. Thanks for watching, and I'll see you in the next one.